Good morning or good evening, whatever time it is, wherever you are. My name is Allison Penko, and I'm at the U.S. Naval Research Laboratory down in southern Mississippi in the United States. And I'm going to talk today about a model that we developed, a seafloor spectral model that we coupled with the spectral model SWAN in order to get predictions of ripple geometry on the seafloor dependent on wave conditions. So I'd like to thank my co-authors, Eric Rogers and Joe Calantoni, for which this work would not happen without them. So I'm first going to talk about the spatial scales of seabed features. These spatial scales vary over a large range, all the way from roughness, what I'm going to call roughness, which is sand grains and sand ripples, all the way up to bathymetry, and by that I mean sandbars. And so different types of forcing cause variations and changes in each of these features. Well, what we're focusing on here with this model is really spatial scales from between about 1 centimeter and a few meters, and that's incorporating ripples that are generated by waves propagating over the seafloor, as well as the biological activity that then have a tendency to degrade the ripples and diffuse them out when the wave actions are low. It's within these spatial scales that the model is applicable. So the Navy has several coupled modeling systems. One in particular couples waves, the atmosphere, ice, and ocean circulation into this large Earth modeling system. However, they really don't incorporate any changes or variations in the seafloor. They treat it as a concrete boundary condition, unchanging, which we know is not true. So what we've been doing in our branch is really focusing on how to get this varying bottom into these coupled modeling systems. And one way to do that is to model the roughness that's changing due to different wave and current conditions. And so that's what the model NSEA is that I'm going to talk about today. And it is a time-dependent spectral approach that is based on the paper in 2007 by Drakowski, and then has been later implemented by Solsby as well as Nelson and Vulgaris. But here we're really just taking wave orbital velocities, wave frequency, and direction, and then the seafloor model NC, which is the Navy seafloor evolution archetype, will predict a seafloor spectra with time, as well as an estimation of sediment transport. So you can really get these wave conditions in from anywhere. We just happen to use the wave model SWAN, which is the Navy's nearshore coastal model. And so we pull in the wave spectra from SWAN and then take the wave orbital velocities that are generated by the peak wave period and significant wave height, and then run these through NC. So of course with SWAN you need boundary conditions, forcing conditions, bathymetry, and then there's several inputs into NC, which include a sediment type. We need suspended and bed load transport equations, a prediction of the equilibrium ripple conditions, which is what the model is being driven towards, and then some understanding or some model of bioturbation. So from here we can predict the seafloor spectra with time. I'm going to go through each of the steps in NC and talk about how this model works. So first we calculate the non-dimensional variables given our Shields parameter. Parameters shown here, not really much new. Mobility, shields, dimensionless grain size. We use the Swart friction factor. But then we also have two critical shields parameters, one for incipient motion, so when the sediment is moving, and then one for sheet flow, which is our critical threshold of when the ripples get washed out. What we do is we look at the shields parameter and compare it to our critical shields parameter for incipient motion. If it is lower, then we know that there is no motion, and therefore the bioturbation kicks in and the ripple heights diffuse out. The bioturbation is using an exponential decay with a diffusion coefficient D, which is taken from Jackson et al. In 2009. The horizontal diffusion coefficient was basically determined from observations of backscatter intensity, and it's within the typical range that Jackson denoted in 2009. But we have a new project starting up here where we're going to look very specifically at exactly what those timescales of evolution are given different bioactivity levels. So next we look if the shield's parameter is greater than the critical shield's parameter, then we know we're in the ripple or the sheet flow. Calculate the sediment transport, which is from Meyer-Peter-Mueller, and realize this is a bedload only transport equation, but it actually works quite well with this. And then we initialize our seafloor spectra with a Gaussian equation that's just based on an initial ripple height and an initial ripple wave number. So now we look at if the shield's parameter is less than the sheet flow critical value. If it is not, then therefore we have ripple washout. So we have sheet flow and we don't have any ripples forming. Our ripple wave number actually goes to 0, which would mean that our ripple wavelength would go to infinity. If the shield's parameter is less than sheet flow, then we know that the seafloor spectra evolves independently with time. To describe that, we basically apply sediment continuity, and the model assumes that the ripples are being driven to the equilibrium ripple spectrum given the instantaneous wave conditions. So over here you show the same equation that you saw for the initial spectrum. It's just using our equilibrium ripple heights and lengths now, which is determined using Nielsen's equilibrium prediction equations. And then we have our seafloor spectra evolution equation here. So this is just saying that the time rate of change of the seafloor spectra is determined by how far the present spectra is from the equilibrium spectra, which is what it's being driven towards, and an adjustment time scale, which is here in the denominator. So the adjustment time scale equation is based on the volumetric sediment transport rate Q, as well as the cross-sectional area of the ripple. So that means that smaller, shorter ripples under higher stresses change faster than larger ripples under low stresses. Using the spectral model allows for each wave number component of the ripple spectrum to evolve independently. So that's NSEA in a nutshell. Basically from there we have our seafloor spectra, and then from that we can take our mean ripple height and length and then parameterize that. First calculate the effective ripple height and length, and that is from the integral under the spectrum. Ripple length is calculated by 2 pi over the mean wave number. And then our roughness length scale is determined on which flow regime we're in. So we're calculating roughness length scale Kn. If we're in the ripple regime, it's based on our ripple height. And if we're in the sheet flow regime, it's based on D50. So from our roughness length scale, we can calculate a new friction factor, which goes into our wave energy dissipation factor. And that is then included as a sinc term in the wave energy density equation in SWAN. So next we're going to compare to some field observations that were taken off the coast of Panama City, Florida in 2013 as part of the ONR and CERTIP-funded target and reverberation experiment. And we're going to look at 2 deployed quad pods, one at 7.5 meters and one at 20 meters. I'm only going to show the 7.5 meter here, but we measured waves, currents, and the seafloor with sector scanning sonar. We run the coupled SWAN NC model using a nested setup. So we start with a 22 kilometer resolution SWAN run, and then we nest all the way down to 444 meters. And it's within this 444 meter resolution domain that we run the coupled SWAN NC. And you can see the 2 red points where we have our quad pods. So what I'm showing here are 2 plots of ripple height on the left and ripple wavelength on the right. And so I'm going to show these in movies, and what you're going to see is the ripple height is going to decrease over time. So that is because when the wave action is low, the bioturbation kicks in and those ripple heights diffuse out. However, you're not going to see any changes in the ripple wavelength unless you get a storm coming through that makes new ripples. And that's because just because the energy in the spectrum is decreasing, our peak wave number for our wavelength is not changing. And so we still see that signal of the ripple wavelength. We're going to see also down at the bottom the time series of ripple height on the left and then ripple length on the right. We unfortunately don't have any observations of ripple height because our pencil beam sonar didn't work, but we have compared to the backscatter intensity of the sonar images, and it matches up pretty well. But this is just showing in time when you get that storm coming through, you get these ripples that are generated out here, and then they just kind of stay there. But as you can see, the ripple heights are diffuse out. Moving on to some quantitative comparisons of the SWAN NC predictions and the observations in black, SWAN NC predictions in blue. So here we're showing wave height, wave period, ripple length, and ripple height. And as you can see, we get pretty good comparisons. The thing to note is that we really do a good job at predicting when the ripples are going to change. And so you can see after the storm comes through, the wave action goes down and then the ripples don't really change. But we do a good job at predicting when they will change. Ripple height, we unfortunately didn't have any measurements of ripple height. That's something we're going to be focusing on in the upcoming project. Over on the right, you see some scatter plots. Our RMSEs are pretty good, 15 centimeters for wave height, 1.4 seconds for wave period. Our ripple length has a small RMSE, but also small correlation. So we're going to be using this model in this upcoming project and really upgrading it, specifically moving on to probabilistic instead of deterministic. And we already have some results that show this. So just in summary, we've developed this time-dependent spectral ripple model coupled with a spectral wave model in order to predict time-dependent seafloor spectra. We've included biological effects using this exponential decay that diffuses out the ripples when the wave action is low. We can use this to be able to predict when ripples will form and their approximate geometry. And we're definitely moving to a more probabilistic modeling framework, and that we can apply in more areas and under different conditions. Some of the things that we've expanded to, we now have a 2D model. We're doing a pretty extensive sensitivity analysis, looking at the effect of the initial parameters and a whole bunch of other really interesting things. So hopefully at ICCE in 2022, I can present that work. So thank you for your time and take any questions.